This is 3ATS, and it's rewriting the textbook on comets faster than we can turn the pages. The story begins on July 1st, 2025, when a telescope in Chile caught something moving against the backdrop of stars. The Asteroid Terrestrial Impact Last Alert System, ATOS for short, spotted an object entering our inner solar system at a distance of 4.5 astronomical units from the Sun. At first, it looked routine. Just another piece of cosmic debris drifting through our neighborhood. The initial data showed a faint point of light moving at what seemed like a normal speed for objects in our solar system. Astronomers logged it as a potential new comet and scheduled follow-up observations. But within hours, that routine classification began to unravel. The first subtle anomaly appeared in the velocity data. When astronomers calculated its speed relative to the Sun, the numbers didn't make sense for a typical solar system object. It was moving too fast. Not just a little fast, impossibly fast. The initial calculations showed it was traveling at nearly 35 kilometers per second. To put that in perspective, that's fast enough to cross the Atlantic Ocean in about 2 minutes. For an object at that distance from the Sun, this speed was anomalous. It suggested this wasn't something that originated in our solar system. The growing realization among astronomers was that this object was fundamentally different from anything we'd seen before. As more data poured in from observatories around the world, the anomalies piled up. The trajectory was wrong. The composition signals were wrong. Even the way it reflected light was wrong. This wasn't just another comet. This was something that had traveled through interstellar space to reach us. The core mystery became clear. We were looking at an object behaving in ways that challenged our fundamental understanding of celestial mechanics. Its hyperbolic orbit meant it wasn't bound to our Sun. Its chemical signatures didn't match any known solar system objects, and its velocity suggested it had been traveling through the galaxy for possibly millions of years before we spotted it. The stakes for planetary science models couldn't be higher. Every comet we've studied until now has been a product of our own solar system's formation. They carry information about how our planets formed, what materials were available in our primordial nebula. But this object, designated 3I Atlas, with the 3I indicating it's only the third confirmed interstellar object, carries information from an entirely different star system. It's a sample from another part of the galaxy, delivered to our doorstep. What we're about to see is how the European Space Agency's reaction to this discovery proves what planetary scientists have feared all along, that we're fundamentally unprepared for what's coming our way from interstellar space. The protocols, the detection systems, the response plans, they were all built around the assumption that threats would come from within our own solar system. 3I Atlas showed us that assumption was dangerously incomplete. What Atlas saw that others missed, the Asteroid Terrestrial Impact Last Alert System, exists for one primary purpose: to give us warning. Operated by the University of Hawaii's Institute for Astronomy, ATLAS consists of 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa, that scan the entire visible sky every night. Their mission is simple but critical: find approaching asteroids before they find us. What makes ATLAS unique isn't its power or precision, but its coverage. While larger telescopes might study specific objects in detail, ATLAS watches everything. It's designed to detect faint, fast, moving objects that other surveys might miss because they're looking elsewhere. This wide field approach is what allowed it to catch 3I Atlas when it did. The specific July 1st observation data tells a story of both capability and luck. The object was detected at magnitude 19.5, faint, but well within ATLAS's detection threshold. What's crucial here is the timing. 3I Atlas was discovered when it was still 4.5 astronomical units from the Sun. That's out near Jupiter's orbit. This early detection gave astronomers precious time to study it before it reached its closest approach to the Sun. The initial velocity and trajectory calculations are what triggered the immediate attention. When astronomers plotted its path, they found it was moving at 34.7 kilometers per second relative to the Sun. But more importantly, they calculated its orbital eccentricity at 1.2. Any number above 1.0 indicates a hyperbolic orbit, an object that isn't gravitationally bound to our solar system. This was the smoking gun. These numbers stood out because they were so different from typical asteroid and comet discoveries. Most objects we find have eccentricities between 0 and 1. They're on elliptical orbits around the Sun. Even long-period comets from the Oort cloud have eccentricities just below 1.0. A value of 1.2 was unprecedented for an object this close to the Sun. The first hints of hyperbolic orbit came from the velocity alone. to achieve that speed at that distance from the Sun, the object would have needed to fall inward from far beyond the gravitational influence of our solar system. There was no way it could have originated within our system and reached that velocity naturally. What ATR saw that others might have missed was the combination of factors: the early detection, the precise velocity measurement, and the immediate recognition that these numbers didn't fit any known category of solar system object. It was the system's design, scanning the whole sky regularly, combined with astronomers' understanding of what normal looks like, that allowed them to identify this anomaly so quickly. Defining the impossible orbit. To understand why 3 Atlas's orbit was so shocking, we need to understand orbital eccentricity in simple terms. Think of eccentricity as a measure of how stretched out an orbit is. A perfect circle has an eccentricity of 0. Most planets have nearly circular orbits with eccentricities close to 0. Comets have more elliptical orbits. They're more stretched out, with eccentricities between 0 and 1. The difference between elliptical and hyperbolic orbits is fundamental. Elliptical orbits are closed loops. Objects follow repeating paths around the Sun. Hyperbolic orbits are open-ended. Objects pass through the solar system once and never return. They're like stones skipping across a pond rather than boats circling in it. Why hyperbolic means interstellar origin is straightforward. Objects can't achieve hyperbolic orbits from within our solar system. The gravity of the Sun ensures that anything born here stays here, unless something gives it an enormous push. To achieve a hyperbolic orbit, an object must come from outside our solar system with enough speed to overcome the Sun's gravitational pull. The initial orbital calculations for 3I's Atlas were jaw-dropping. With an eccentricity of 1.2, it was unequivocally on a hyperbolic trajectory. But what made it even more remarkable was its orientation. The orbit was inclined nearly 45 degrees to the plane of the solar system. It was coming in from above, not from within the ecliptic plane where most solar system objects reside. Comparing to Oumuamua's trajectory reveals both similarities and crucial differences. Oumuamua, discovered in 2017, had an eccentricity of about 1.2 as well, but it was detected much closer to the Sun and was already on its way out. 3I Atlas was detected earlier in its approach, giving us more time to study it. More importantly, 3I Atlas showed clear cometary activity, outgassing, while Oumuamua did not. The statistical improbability of such orbits is what makes them so significant. Before Oumuamua, we had never confirmed an interstellar object. Now we have 3 in just a few years. Either we've been incredibly lucky, or these objects are more common than we thought. The math suggests that for us to detect 2 such objects in such a short time, there must be thousands of them passing through our solar system undetected every year. Why this already challenged existing models is because our theories of planetary system formation didn't predict this frequency. We thought ejecting objects from other star systems would be rare. The discovery of 3I Atlas suggests that either planetary systems are much more violent than we thought, ejecting material frequently, or that the interstellar medium is denser with such objects than our models accounted for. The first chemical signature, the early spectroscopic observations, began almost immediately after discovery. Astronomers pointed some of the world's most powerful telescopes at this faint speck of light, breaking its light into spectra that would reveal its chemical composition. What they found was both familiar and strange. The initial detection of carbon dioxide was expected. Most comets contain CO2. But the surprising intensity of outgassing was not. At 4.5 astronomical units from the Sun, most comets are still frozen solid. The sunlight isn't intense enough to cause significant sublimation of ices. Yet 3I Atlas was already showing strong emission lines indicating active outgassing. Comparing to typical comet sublimation patterns reveals how anomalous this was. A solar system comet at that distance would have a coma, the cloud of gas and dust around the nucleus, measuring perhaps a few thousand kilometers across. 3I's Atlas coma was already over 50,000 kilometers across. It was behaving like a comet near perihelion, not one still out near Jupiter. The anomaly of activity at that distance raised immediate questions about the object's composition. Was it made of more volatile ices than solar system comets? Did it have a different internal structure that allowed heat to penetrate more effectively? Or was there some other energy source at work? What the CO2 ratio suggested about composition was particularly intriguing. The ratio of carbon dioxide to other volatiles was different from anything we've seen in solar system comets. It suggested that either the protoplanetary disk where 3I Atlas formed had different chemical abundances than ours, or that its long journey through interstellar space had altered its surface chemistry. These first questions about internal structure would become central to understanding the object. If it was outgassing so vigorously so far from the Sun, what did that imply about its porosity? About the distribution of ices within it? About its overall strength and cohesion? The answers to these questions would not only help us understand this particular object, but would inform our models of how planetary systems form around other stars. ESA's initial assessment, the European Space Agency's Planetary Defense Office, received the initial data within hours of the discovery. Their response protocol for interstellar objects was, frankly, underdeveloped. The framework existed mainly as a theoretical exercise, something to discuss at conferences rather than an operational plan. How ESA first engaged with the data followed their standard threat assessment workflow. The first step was orbit determination. Was this object a potential impact threat? The initial calculations showed it would pass safely by Earth, but the margin was concerning. The uncertainty in its trajectory at that distance meant the probability of impact wasn't zero. It was around 0.01%, small but not negligible for an object of this size. The standard protocol for interstellar objects was essentially the same as for near-Earth objects: calculate the orbit, assess the impact probability, monitor for changes. But 3i Atlas didn't fit the classification system neatly. It was too active for an asteroid, but its orbit was wrong for a comet. Its velocity was wrong for a solar system object. Nothing in their playbook prepared them for an object that broke multiple categories at once. Why 3i Atlas didn't fit the classification became apparent as more data arrived. The object was showing cometary activity, but had the orbit of an interstellar asteroid. Its light curve suggested an elongated shape like Oumuamua, but it was much more active. Every new observation seemed to add another layer of mystery rather than resolving the existing ones. The early internal discussions and concerns focused on two main issues: the object's potential as an impact threat and its value as a scientific specimen. The impact probability, while low, was high enough to warrant serious attention given the object's size and velocity. But equally concerning was the fact that we might be about to lose a unique opportunity to study material from another star system. Comparing to Oumuamua response protocols revealed how much had changed in just a few years. With Oumuamua, the response was primarily scientific curiosity. With 3i Atlas, there was a palpable sense of urgency driven by the recognition that we might only get one chance to study it properly. The decision to monitor rather than announce was strategic. ESA, in coordination with NASA and other space agencies, chose to gather more data before making any public statements. They needed better trajectory calculations, better size estimates, better composition analysis. But this cautious approach would soon be tested as the object revealed more of its secrets. First indications this required special handling came from the velocity refinements. As tracking continued, the object's speed kept coming in higher than initial estimates. It was moving faster than any natural object we'd seen at that distance from the Sun. This alone made it worthy of heightened attention, but what came next would force a complete re-evaluation of the threat level. The velocity problem, the precise velocity measurements kept refining, and each update made the situation more extraordinary. By the time the object reached 3 astronomical units from the Sun, astronomers had pinned its velocity at 35.2 kilometers per second with an uncertainty of just 0.1 kilometers. This precision matters because it's how velocity confirms interstellar origin beyond any reasonable doubt. Think about escape velocity, the speed needed to break free from the Sun's gravity. At Earth's distance, that's about 42 km. But 3i Atlas was measured further out, where the Sun's gravitational grip is weaker. The escape velocity at 3AU is approximately 24 km. 3i Atlas was moving 11 km faster than needed to escape our solar system entirely. This isn't just fast. It's impossibly fast for an object that originated within our solar system. The impossible speed relative to our solar system becomes clear when you consider the energy requirements. To achieve that velocity naturally within our system, an object would need to have received a gravitational slingshot from Jupiter or Saturn. But the trajectory showed no recent encounters with giant planets. The velocity was intrinsic to the object. It entered our system with that speed. Comparing to escape velocity of the solar system from infinity, about 42 km, shows that 3i Atlas was moving at 84% of the velocity needed to escape from the interstellar medium itself. This is what made atmospheric entry studies so urgent. If this object were on a collision course with Earth, it would strike our atmosphere at over 35 km. For comparison, most asteroids hit at 15 to 20 km. The energy release would be proportional to the square of the velocity, meaning this would pack 3 to 4 times the destructive power of a typical impactor of the same mass. What the velocity implied about galactic travel is equally fascinating. This object has been moving through the galaxy for millions of years. At 35 kilometers, it could travel from one side of the galaxy to the other in about 1 billion years. But more immediately, it told us about the environment it came from. To achieve that velocity naturally, it would need to have been ejected from its home star system during the chaotic planet-forming period, likely by interactions with giant planets. The energy requirements for such speed are enormous. The kinetic energy of a 1-kilometer object moving at 35 km is equivalent to about 50 megatons of TNT per kilogram for an object the size of 3I Atlas, estimated at 1.5 kilometers in diameter. The total kinetic energy was comparable to the largest nuclear weapons ever built, but multiplied by millions. This is why the velocity problem wasn't just an academic curiosity, it was a planetary defense concern of the highest order. Why this made atmospheric entry studies urgent became ESA's immediate focus. They needed to model what would happen if, against the odds, this object did intersect Earth's orbit. The high velocity meant it would penetrate deeper into the atmosphere before disintegrating. It would convert its enormous kinetic energy into heat more efficiently. And if it contained unusual materials, it might behave differently than typical asteroids or comets during atmospheric entry. Chemical composition deep dive, the advanced spectroscopic analysis began in earnest as the object approached 2.5 astronomical units from the Sun. Using the Very Large Telescope in Chile and the Keck Observatory in Hawaii, astronomers obtained high-resolution spectra that revealed details nobody expected. The detection of water-ice signatures was both expected and surprising. Expected because most comets contain water ice. Surprising because the ratio of water to other volatiles was wrong. In typical solar system comets, water is the dominant volatile, making up about 80% of the ices. In 3I Atlas, water accounted for only about 50% of the outgassing. The rest was primarily carbon dioxide, with traces of carbon monoxide and other compounds. The carbon dioxide to water ratio anomaly was the most significant finding. While solar system comets typically have CO2-H2O ratios around 10–20%, 3I Atlas showed a ratio approaching 50%. This suggested it formed in a much colder environment than typical solar system comets, perhaps further from its parent star, or in a protoplanetary disk with different thermal conditions. Searching for complex organic molecules yielded both expected and unexpected results. The spectra showed clear signatures of methanol and formaldehyde, common in solar system comets, but also showed unusual absorption features around 3.4 micrometers that suggested the presence of more complex organic compounds. These features matched what we'd expect from tholins, complex organic polymers formed by irradiation of simple ices. But the intensity of these features was stronger than in any solar system comet we've studied. The absence of expected dust particles was equally puzzling. As a comet approaches the Sun and heats up, it should release dust along with gases. The dust creates the visible coma and often forms tails, but 3I's Atlas showed remarkably little dust for its level of gas production. The dust-to-gas ratio was about 1/10 what we'd expect from a solar system comet with similar activity. Comparing to solar system comet compositions reveals how fundamentally different 3I Atlas was. It wasn't just a matter of having different proportions of the same ingredients. It seemed to be made of different ingredients altogether. The chemical fingerprints suggested it formed in an environment with different elemental abundances, or perhaps at a different time in galactic evolution when the interstellar medium had a different composition. What the unique mix suggested about origin points to several possibilities. The high CO2 content could indicate formation in the outer regions of a protoplanetary disk, where temperatures were cold enough for CO2 ice to condense efficiently. The unusual organic signatures might suggest exposure to different radiation environments during its journey. But the most compelling interpretation was that 3I Atlas formed around a different type of star than our Sun. Perhaps a star with different metallicity, or in a binary system where chemical mixing occurred differently. The implications for planetary science are profound. If this composition represents what's typical in other planetary systems, then our solar system might be the outlier, or perhaps there's much greater diversity in comet compositions than we imagined. Either way, 3I Atlas was showing us that the building blocks of planets can vary significantly from one star system to another. The light curve mystery The unexpected brightness variations began to appear as astronomers collected photometric data over several nights. The object wasn't just getting brighter as it approached the sun. It was fluctuating in strange, unpredictable ways. Analyzing the rotation period proved challenging because the variations weren't periodic in the way we'd expect from a rotating body. Most asteroids and comets show regular brightness changes as they spin, with periods ranging from hours to days. 3i Atlas showed some periodic variation, suggesting a rotation period of about 8 hours, but superimposed on this were larger, irregular dimming events that didn't repeat. The strange non-periodic dimming was the real mystery. Sometimes the object would drop in brightness by 20–30% over a few hours, then recover just as quickly. These events weren't correlated with the rotation period, and they didn't follow any obvious pattern. They suggested that something was intermittently blocking our view of the nucleus. But what? Comparing to Oumuamua's light curve reveals both similarities and differences. Oumuamua showed extreme brightness variations, suggesting a highly elongated shape, but its variations were periodic and predictable. 3i Atlas variations were more chaotic, suggesting either a more complex shape or some active process was occurring. Possible explanations for the fluctuations ranged from the mundane to the extraordinary. The simplest explanation was that we were seeing large chunks of material being ejected from the nucleus, temporarily blocking light. Another possibility was that the nucleus had an extremely irregular shape with both convex and concave regions, causing complex light scattering. More speculative ideas included the possibility of precession, where the rotation axis itself was changing, or even that we were seeing evidence of fragmentation. What the light curve revealed about shape was particularly intriguing. The overall amplitude of variation, about 1.5 magnitudes, suggested an elongated object with an axis ratio of at least 4:1. This would make it even more elongated than Oumuamua, which had an estimated ratio of about 6:1. Such extreme elongation is rare among solar system objects and suggests a unique formation history. Implications for structural integrity came from the combination of the elongation and the outgassing activity. Typically, comets with such vigorous activity are more spherical because outgassing tends to round them off over time. The fact that 3i Atlas maintained such an elongated shape despite its activity suggested it was made of stronger material than typical comets, perhaps more like a rocky asteroid than an icy comet. The light curve mystery ultimately pointed to an object that defied easy classification. It had aspects of both comets and asteroids, but didn't fit neatly into either category. This ambiguity would become a recurring theme as we learned more about 3i Atlas. Every new observation seemed to deepen the mystery rather than resolve it. Trajectory refinement and concerns the updated orbital calculations from new data began to paint a worrying picture. As tracking continued through August and September 2025, the uncertainty in the object's path decreased, but the refined trajectory showed it passing closer to Earth than initially estimated. The improving precision of the path prediction came from several factors: more observational data points, longer baseline observations, and improved modeling of non-gravitational forces. The outgassing from 3i Atlas was affecting its trajectory in subtle ways, something that's common with active comets but difficult to model accurately. How small uncertainties become major concerns is a fundamental challenge in orbital mechanics. When you're dealing with an object moving at 35 km/s, a tiny angular uncertainty translates to a large positional uncertainty months later. Initially, the uncertainty ellipse, the region where the object might actually be, was millions of kilometers across. As observations continued, this ellipse shrank, but it still encompassed worrisome possibilities. The gravitational keyholes it would pass through became a particular concern. A gravitational keyhole is a region in space where a planet's gravity can significantly alter an object's future trajectory. 3i Atlas was going to pass through several such regions near Jupiter and Saturn, and even a very close approach to Mars. Each keyhole encounter introduced new uncertainties into long-term predictions. The near misses with major planets were both scientifically valuable and concerning from a planetary protection standpoint. The close approach to Mars, within 500,000 kilometers, would provide an excellent opportunity for observation, but it also meant Mars' gravity would bend the trajectory slightly. The subsequent Jupiter encounter, while further away, would have an even greater effect due to Jupiter's massive gravity. Why the path was becoming more worrying wasn't about immediate impact risk. The probability of Earth impact remained extremely low. The concern was about what the refined trajectory told us about future returns. With each gravitational encounter, 3I's Atlas orbit was being changed in ways that made predicting its long-term behavior increasingly difficult. There was a small but non-zero chance that after its tour through the inner solar system, it could be perturbed into an orbit that would bring it back toward Earth in the distant future. The first serious discussions about deflection began in September 2025, not because anyone thought deflection was necessary for this pass, but because the exercise revealed gaps in our preparedness. If an object like 3I Atlas were on a collision course, did we have the capability to deflect it? The high velocity made traditional deflection methods much less effective. Kinetic impactors would need to be much larger or faster. Gravity tractors would need much more time. The discussions forced a reckoning with our planetary defense capabilities. The dust dilemma, the expected dust production versus reality, became increasingly puzzling as 3I's Atlas continued its approach. By the time it reached 2 astronomical units from the Sun, it should have been producing a significant dust tail. Instead, the dust production remained anomalously low. The peculiar size distribution of particles that were present added another layer of mystery. Most comets produce dust across a range of sizes, from microscopic grains to centimeter-sized particles. The dust from 3I Atlas seemed to be dominated by very small particles, sub-micron in size, with almost no larger grains. This was the opposite of what we typically see. How the dust trail differed from predictions became apparent when astronomers compared their models to actual observations. Standard comet models predicted a dust tail pointing away from the Sun, created by radiation pressure on the small particles. 3I Atlas dust tail was much narrower and more collimated than expected, suggesting the dust particles had different properties, perhaps different composition or structure than typical comet dust. Implications for the object's age and history emerged from the dust properties. The absence of larger grains could mean that 3I Atlas had been stripped of its surface layers during its long journey through interstellar space. Cosmic rays and interstellar dust impacts might have sandblasted the surface, leaving only the smallest particles behind. Alternatively, it might have formed without larger dust grains to begin with. What the dust revealed about formation environment pointed to conditions different from our solar system. The dominance of small particles suggested either that the protoplanetary disk, where it formed, had different dust grain sizes, or that the processes that normally produce larger grains in comets operated differently there. Why the lack of dust was scientifically troubling goes beyond mere curiosity. Dust plays a crucial role in how comets behave. It helps regulate temperature, it affects outgassing patterns, and it provides information about formation conditions. The anomalous dust properties of 3I Atlas meant that many of our standard tools for analyzing comets might not apply. We were essentially flying blind, trying to interpret an object that didn't follow the rules we've come to expect. Connecting dust properties to origin theories led to several competing hypotheses. One school of thought suggested that 3I Atlas originated in a debris disk around an older star, where collisions had ground down most material to small sizes. Another proposed that it came from a system with much stronger radiation pressure, which blew away larger grains during formation. A third possibility was that we were seeing the effects of prolonged exposure to the interstellar medium, a kind of cosmic weathering that had altered the surface properties. The dust dilemma ultimately highlighted how much we still have to learn about the diversity of small bodies in the galaxy. Each new interstellar object we discover seems to present us with a new set of puzzles, challenging our assumptions and forcing us to reconsider what we thought we knew about how planetary systems form and evolve. Thermal modeling discrepancies. How scientists model heat absorption in comets is based on decades of studying solar system objects. We understand how different materials absorb and radiate heat, how rotation affects temperature distribution, and how outgassing can cool the surface. But 3I Atlas challenged all these assumptions. Predictions versus actual temperature readings revealed significant discrepancies. Based on its distance from the Sun and its albedo, how reflective it is, scientists predicted the surface temperature should be around 150 Kelvin, 123 degrees C. Actual measurements from infrared telescopes showed temperatures closer to 180 Kelvin, 93 degrees C. This 30-degree difference might not sound like much, but in the cold of space, it's enormous. The anomaly of uneven heating was even more puzzling. As the object rotated, different parts should heat and cool predictably. Instead, the temperature variations across the surface were much smaller than expected. Some areas that should have been in shadow remained surprisingly warm, while sunlit regions weren't as hot as they should have been. What the thermal data said about surface properties pointed to several possibilities. The most likely explanation was that the surface had very low thermal inertia, meaning it didn't conduct heat well. This is typical of porous, fluffy surfaces like those found on comets. But the magnitude of the effect was greater than anything we've seen in solar system comets, suggesting an extremely porous surface, perhaps with unusual material properties. Comparing to known asteroid and comet types revealed that 3I's Atlas didn't match any established category. Its thermal behavior was somewhere between a typical comet and a rare type of asteroid known as a rubble pile, an object made of loosely bound material. But even rubble pile asteroids show more predictable thermal behavior. Why the thermal behavior didn't match any category became clearer when combined with other observations. The low dust production, the vigorous outgassing, the elongated shape, all suggested an object with unique physical properties. Perhaps it had a fractal-like structure with enormous surface area, or maybe it contained materials with unusual thermal properties not found in our solar system. Implications for material strength and composition were significant for planetary protection considerations. If the object had low thermal inertia and high porosity, it might be structurally weak, prone to breaking up during atmospheric entry. This could be both good and bad news. Good because fragmentation reduces the risk of a single large impact, bad because multiple fragments spreading over a large area could cause wider damage. The thermal modeling discrepancies ultimately forced a re-evaluation of how we predict the behavior of unknown objects entering our solar system. Our models, built on experience with solar system objects, might not apply to visitors from other star systems. This realization had immediate implications for how ESA assessed the threat posed by 3I Atlas and how they would need to adjust their protocols for future interstellar objects. The rotation rate anomaly measuring the spin period precisely required combining data from multiple observatories over several weeks. The result was both surprising and illuminating. 3I Atlas was rotating with a period of 7.9 hours, but with remarkable stability. The unexpected stability of rotation was the first anomaly. Most active comets show changes in their rotation period over time due to outgassing. As gas jets escape from the nucleus, they act like tiny rockets, applying torque that can speed up or slow down the rotation. 3I Atlas showed no detectable change in its rotation period over 2 months of observation. Highly unusual for such an active object. Lack of non-gravitational acceleration was related to the rotation stability. The same outgassing that affects rotation also affects the object's trajectory through what's called the rocket effect. Yet precise tracking showed that 3I Atlas was following a purely gravitational orbit. The outgassing wasn't producing measurable changes in its path. This was strange because at its level of activity, we would expect significant non-gravitational forces. Comparing to typical comet rotation behavior highlighted how anomalous this was. Most comets have rotation periods between 6 and 20 hours, but they're constantly changing due to outgassing. Some comets even tumble chaotically rather than rotating smoothly. 3I Atlas, stable rotation, suggested either that the outgassing was perfectly symmetrical, unlikely given its elongated shape, or that the object had such high mass that the outgassing torques were negligible in comparison. What the spin rate revealed about mass distribution was particularly interesting. The stability of rotation suggested that the mass was distributed in a way that minimized the effects of outgassing. Perhaps the object was rotating around its maximum moment of inertia, the most stable configuration, or maybe the outgassing was occurring from regions that didn't apply significant torque. Why the rotation-challenged formation models goes back to how we think objects like this form. If 3I Atlas formed through accretion in a protoplanetary disk, we'd expect it to have a more irregular rotation, perhaps influenced by collisions during formation. Its stable rotation suggests either a very gentle formation process or subsequent processing that regularized its spin. Implications for the object's structural integrity came from combining the rotation data with the shape information. An elongated object rotating stably suggests it has sufficient internal strength to maintain its shape against centrifugal forces. If it were a loose pile of rubble, we'd expect it to reshape itself into a more spherical form over time. The fact that it maintained its elongated shape while rotating stably suggested stronger internal cohesion than typical comets. The rotation rate anomaly ultimately pointed to an object with unusual internal properties. It wasn't just a simple ball of ice and rock. It had structure, strength, and stability that belied its active appearance. This combination of characteristics would become central to understanding why ESA's reaction to 3i Atlas was so different from their response to previous interstellar objects. Gravitational interactions analysis modeling encounters with Jupiter's gravity became a priority as 3i Atlas approached the giant planet's orbit. Even though the closest approach was still millions of kilometers away, Jupiter's massive gravity would have a significant effect on the trajectory. How slight changes amplified uncertainties is a fundamental aspect of orbital mechanics. The exact distance at which 3i Atlas would pass Jupiter was uncertain by tens of thousands of kilometers. A small error in percentage terms, but enough to change the outcome significantly. Each minute of arc uncertainty in the initial observations translated to thousands of kilometers of uncertainty at the encounter distance. The keyhole concept and its implications became a major concern in the risk assessment. A gravitational keyhole is a specific region near a planet where the gravity will bend an object's trajectory in such a way that it returns to hit Earth on a future orbit. For 3i Atlas, there were several keyholes near Jupiter that, if passed through, could potentially make it a threat to Earth in the distant future. Calculating probability of Earth encounter required running thousands of simulations with slightly different initial conditions. The results showed that while the probability of impact on this pass was negligible, less than 1 in a billion, the probability of entering an Earth crossing orbit after gravitational interactions with Jupiter was around 0.1%. This might sound small, but for an object of this size and velocity, it was concerning enough to warrant serious attention. Why even tiny probabilities required attention comes down to the consequences. An impact by an object moving at 35 km/h would release energy equivalent to thousands of nuclear weapons. Even a 0.1% chance of such an event occurring in the future justifies significant effort to understand and mitigate the risk. How the gravity assists change the long-term path was both scientifically interesting and concerning from a planetary defense standpoint. The encounters with Jupiter and Saturn were bending 3i Atlas' trajectory significantly. Instead of continuing on a roughly straight path through the solar system, it was being redirected. Its future path now depended critically on the exact geometry of these encounters. The growing concern about future returns emerged from these calculations. While 3i Atlas posed no immediate threat, there was a real possibility that after its interactions with the giant planets, it could be placed on an orbit that would bring it back toward the inner solar system in a few hundred or thousand years. And if that happened, the uncertainties in its future position would be enormous, making it difficult to predict whether it would pose a threat to Earth. The gravitational interactions analysis ultimately forced ESA to consider scenarios they had previously thought were purely theoretical. The combination of high velocity, unusual composition, and complex gravitational interactions made 3i Atlas a unique case study in interstellar object dynamics, one that would inform planetary defense strategies for decades to come. Comparison to solar system objects, the detailed comparison to known comets, revealed just how unusual 3i Atlas was. Solar system comets fall into two main categories: short-period comets from the Kuiper belt and long-period comets from the Oort cloud. 3i Atlas didn't fit either category. How 3i Atlas differed from Kuiper belt objects was particularly striking. Kuiper belt objects tend to have more circular orbits and different chemical compositions. They're also generally less active than 3i Atlas was at similar distances from the Sun. The high carbon dioxide content and unusual dust properties of 3i Atlas had no parallel in our database of Kuiper belt objects. Contrasting with Oort cloud comet properties highlighted different anomalies. Oort cloud comets do show high activity levels, but their compositions are more similar to each other than to 3i Atlas. The specific ratio of carbon dioxide to water, the types of organic compounds present, and the dust properties all marked 3i Atlas as fundamentally different from any Oort cloud comet we've studied. What the differences revealed about formation was the most significant insight. Since Oort cloud comets formed in our solar system's outer regions, they carry information about conditions in our primordial solar nebula. 3i Atlas, by contrast, carries information about a completely different formation environment. The differences suggest that either the protoplanetary disk, where it formed, had different conditions, or that it formed at a different time in galactic evolution when the interstellar medium had different composition. Why it couldn't be classified with existing categories became increasingly clear as more data accumulated. The International Astronomical Union has specific definitions for comets, asteroids, and other small bodies, But 3-Eiger Atlas didn't fit neatly into any of them. It had aspects of each comparison to solar system objects. The detailed comparison to known comets revealed just how unusual 3-Eiger Atlas was. Solar system comets fall into two main categories: short-period comets from the Kuiper belt and long-period comets from the Oort cloud. 3-Eiger Atlas didn't fit either category. How 3-Eiger Atlas differed from Kuiper belt objects was particularly striking. Kuiper belt objects tend to have more circular orbits and different chemical compositions. They're also generally less active than 3-Eiger Atlas was at similar distances from the Sun. The high carbon dioxide content and unusual dust properties of 3-Eiger Atlas had no parallel in our database of Kuiper belt objects. Contrasting with Oort cloud comet properties highlighted different anomalies. Oort cloud comets do show high activity levels, but their compositions are more similar to each other than to 3-Eiger Atlas. The specific ratio of carbon dioxide to water, the types of organic compounds present, and the dust properties all marked 3-Eiger Atlas as fundamentally different from any Oort cloud comet we've studied. What the differences revealed about formation was the most significant insight. Since Oort cloud comets formed in our solar system's outer regions, they carry information about conditions in our primordial solar nebula. 3-Eiger Atlas, by contrast, carries information about a completely different formation environment. The differences suggest that either the protoplanetary disk where it formed had different conditions, or that it formed at a different time in galactic evolution when the interstellar medium had different composition. Why it couldn't be classified with existing categories became increasingly clear as more data accumulated. The International Astronomical Union has specific definitions for comets, asteroids, and other small bodies, but 3-Eiger Atlas didn't fit neatly into any of them. It had aspects of each category while belonging to none. This classification problem wasn't just academic. It had practical implications for how different space agencies should respond, what protocols should be triggered, and how resources should be allocated. The implications for planetary system formation theories were profound. Our current models are based on the assumption that our solar system is typical, that the processes that formed our planets, asteroids, and comets operate similarly around other stars. 3-Eiger Atlas challenged that assumption. Its unique properties suggested that either planetary formation is more diverse than we thought, or that our solar system is actually the outlier. How it challenged our understanding of typical compositions goes to the heart of comparative planetology. We've built our understanding of how planetary systems work by studying our own solar system. But if the building blocks, the comets and asteroids, are fundamentally different in other systems, then the planets that form from them might be different too. 3-Eiger Atlas was giving us our first direct evidence that the materials available for planet formation can vary significantly from one star system to another. The classification dilemma ultimately forced a broader discussion about how we categorize celestial objects. The existing system, built around solar system objects, might be inadequate for dealing with the diversity we're now discovering in interstellar space. This realization would have lasting implications for how we organize our knowledge and plan our exploration strategies. The interstellar medium signature, analyzing the object for interstellar travel effects, became a priority as astronomers realized they had a unique opportunity. 3-Eiger Atlas had been traveling through the galaxy for millions of years, and its surface should carry signatures of that journey. Searching for evidence of cosmic ray bombardment was one approach. Cosmic rays, high-energy particles from throughout the galaxy, constantly bombard objects in space. Over millions of years, this bombardment can create unique isotopic signatures and alter surface materials. The question was whether we could detect these effects remotely. What the surface could reveal about galactic environment was particularly exciting. Different regions of the galaxy have different densities of cosmic rays, different abundances of elements, and different levels of interstellar dust. If we could read the signatures on 3-Eiger Atlas's surface, we might learn about the regions of space it had traveled through. Comparing to predictions for interstellar travelers revealed both matches and mismatches. Models predicted that long-term exposure to the interstellar medium should create a kind of space weathering, a darkening and reddening of the surface due to radiation damage. 3-Eiger Atlas showed some of these effects, but not to the degree expected given its estimated travel time. The absence of expected erosion patterns was puzzling. Based on its estimated age and travel distance, astronomers expected to see more evidence of micrometeorite impacts and radiation damage. The relatively pristine appearance of the surface suggested either that the object was younger than estimated, or that the interstellar medium in its travel path was less dense than in our local region. Implications for the object's age and travel distance became a subject of intense debate. If the surface showed less weathering than expected, perhaps 3i Atlas hadn't been traveling as long as we thought. Alternatively, maybe it had taken a path through regions of space with lower density of interstellar material. Either possibility had implications for how common such objects might be, and how often we should expect to see them. What it suggested about the density of interstellar space was equally important. Our models of the galactic environment are based on limited observations. 3i Atlas provided a unique probe of conditions along its travel path. The relative lack of weathering suggested that the interstellar medium might be less dense in some regions than our models predict, or that the object had some mechanism for renewing its surface. The interstellar medium signature analysis ultimately provided a new way to study our galaxy. Instead of looking out from our solar system, we could study the signatures imprinted on visitors from elsewhere. This reverse perspective, using incoming objects as probes of distant regions, opened up new possibilities for galactic astronomy. The data from 3i's Atlas would help refine our models of the interstellar medium, with implications for everything from the design of future interstellar missions to our understanding of how material moves between star systems. It was a reminder that sometimes the most valuable scientific instruments are the ones nature delivers to our doorstep. Internal structure theories modeling based on rotation and outgassing data allowed scientists to probe 3i Atlas' internal structure without ever touching it. The combination of stable rotation, vigorous outgassing, and elongated shape pointed to a complex internal architecture. The possibility of a fractured interior emerged from the outgassing patterns. Most comets have relatively homogeneous interiors, but 3i Atlas gas production seemed to come from specific regions rather than being evenly distributed. This suggested that the interior might be fractured, with volatile, rich pockets separated by more solid material. Theories about primordial structure preservation were particularly intriguing. Some researchers suggested that 3i Atlas might represent a primordial planetesimal, a building block of planets that had never been significantly altered since its formation. Its unusual properties could reflect conditions in the protoplanetary disk where it formed, preserved essentially unchanged for billions of years. How the internal composition affects survival during interstellar travel was a key consideration. Objects traveling through space face numerous hazards: radiation, micrometeorite impacts, temperature extremes. An object with strong internal structure would be more likely to survive these challenges intact. 3i Atlas' apparent resilience suggested it had robust internal cohesion. Implications for carrying organic material were significant for astrobiology. If 3i Atlas had protected interior regions, it might be carrying complex organic compounds from its home system. The detection of unusual spectral features already hinted at this possibility. A fractured interior with protected pockets could preserve these materials even during long interstellar journeys. What the structure revealed about formation process pointed to several possibilities. The elongated shape suggested formation through gentle accretion rather than violent collisions. The stable rotation indicated a coherent internal mass distribution. Together, these clues painted a picture of an object that formed in a relatively calm environment, possibly far from the chaotic region where planets were forming. Why internal structure matters for planetary protection became clear when considering potential impact scenarios. An object with strong internal cohesion would behave differently during atmospheric entry than a fragile comet. It might penetrate deeper before fragmenting, or it might maintain its integrity all the way to the ground. Understanding the internal structure was therefore crucial for assessing the threat level and planning mitigation strategies. The internal structure theories ultimately highlighted how much we can learn from remote observations. By combining data from different sources, light curves, spectroscopy, thermal measurements, we can build detailed models of an object's interior without ever getting close to it. This capability would prove invaluable as 3i Atlas continued its journey through our solar system. Historical context of interstellar objects Oumuamua and what we learned from it provided the essential background for understanding 3i Atlas. Discovered in 2017, Oumuamua was our first confirmed interstellar visitor, and it challenged many assumptions about what such objects would be like. Previous false alarms and misclassifications reminded us that identifying interstellar objects is tricky. Several objects initially thought to be interstellar were later reclassified as unusual solar system objects. This history made astronomers cautious about declaring 3I Atlas interstellar until the evidence was overwhelming. How our detection capabilities have improved since Oumuamua was significant. In just 8 years, our survey telescopes had become more sensitive, our follow-up capabilities had expanded, and our understanding of what to look for had matured. This improvement explained why we were finding more interstellar objects. We were getting better at detecting them. Why 3I Atlas represents a new category became clear through comparison. Oumuamua was small, showed no cometary activity, and had an unusual elongated shape. 3I Atlas was larger, highly active, and had different composition. The two objects were as different from each other as they were from solar system objects, suggesting that interstellar visitors might be quite diverse. The evolution of interstellar object science has been rapid. Before 2017, the field was largely theoretical. Now we had actual data from multiple objects, and each new discovery was forcing us to revise our theories. The pace of discovery suggested that we were only seeing the tip of the iceberg, that many more interstellar objects pass through our solar system undetected. What each discovery has taught us is that our solar system is not an island. Material moves between star systems, and we're constantly receiving visitors from elsewhere in the galaxy. This realization has profound implications for everything from planetary formation theories to the possibility of panspermia, the transfer of life between star systems. How 3I Atlas changes the expected frequency is perhaps its most important contribution to the field. With 2 confirmed interstellar objects in 8 years, astronomers have been able to make better estimates of how common such visitors are. The current best estimate is that there are always several interstellar objects within Neptune's orbit, most too faint for us to detect. The historical context reminds us that we're living through a revolution in our understanding of the solar system's place in the galaxy. Each new interstellar discovery adds another piece to the puzzle, helping us understand how material moves through the galaxy and how planetary systems interact with each other. Planetary Protection Protocols, ESA's existing planetary protection framework was designed primarily for dealing with solar system objects. The protocols assumed that any threat would come from within our own system, where we have some understanding of the materials and dynamics involved. How protocols are triggered depends on the estimated size of the object and its probability of impact. For solar system objects, there are well-established thresholds. If an object larger than a certain size has more than a certain probability of impact, specific response protocols are activated. The decision matrix for potential threats involves multiple factors: size, velocity, composition, impact probability, and warning time. Each factor is weighted differently, and the combination determines the level of response. For 3I Atlas, several factors fell outside the normal ranges, making the decision process more complex. When public notification is required is a delicate balance. Too early, and you risk causing unnecessary alarm if the threat diminishes with better data. Too late, and you lose the opportunity for preparation and mitigation. For interstellar objects, this balance is even trickier because of the additional uncertainties. The balance between transparency and panic is always a concern in planetary defense. The public has a right to know about potential threats, but premature or poorly communicated information can cause unnecessary fear. ESA's approach has generally been to err on the side of caution, providing information only when it's well vetted and accompanied by clear context. How 3I Atlas fit into the existing system revealed gaps in our preparedness. The high velocity, unusual composition, and interstellar origin all fell outside the parameters for which the protocols were designed. This forced ESA to adapt their procedures in real time, creating a new template for dealing with future interstellar objects. Why this case required new thinking became apparent as more data came in. The standard approaches for risk assessment and mitigation didn't apply neatly to an object moving at 35 km with unknown material properties. ESA had to develop new models, new assessment criteria, and new response strategies specifically for this type of threat. The Planetary Protection Protocol's evolution triggered by 3I Atlas would have lasting implications for how we prepare for future interstellar visitors. The experience showed that we need to think beyond the assumptions built into our current systems and develop more flexible approaches that can handle the unexpected. The communication dilemma: internal debates about public disclosure began almost immediately after the orbital parameters were confirmed. On one side were those who argued for immediate transparency. The public had a right to know about such a significant discovery. On the other were those who advocated for waiting until more data was available to avoid causing unnecessary concern. The scientific community's divided opinions reflected broader tensions in how to handle potentially alarming discoveries. Some researchers argued that all data should be released immediately to maximize scientific progress. Others worried that raw data without proper context could be misinterpreted or sensationalized. Balancing public interest with potential concern was particularly challenging given the object's high velocity and unusual properties. While the impact probability was low, the consequences of an impact would be catastrophic. Communicating this balance accurately without either minimizing the risk or causing panic required careful wording. How previous announcements were handled provided both guidance and cautionary tales. The announcement of Oumuamua had been relatively low-key, treated primarily as a scientific curiosity. But 3i Atlas was different, larger, faster, and showing unexpected behavior. The response needed to be proportional to the actual risk while acknowledging the unique nature of the object. The unique challenges of 3i Atlas included its ongoing changes in behavior. As it approached the Sun, its activity levels increased, its trajectory refined, and new anomalies appeared. This meant that any communication would quickly become outdated, requiring constant updates and refinements. The decision timeline and key moments were dictated by the object's motion. As it moved closer to Earth's orbit, the window for making decisions narrowed. Key milestones included the refinement of the impact probability below specific thresholds, the detection of new chemical signatures, and the results of gravitational interaction calculations. What influenced the communication strategy ultimately was a combination of factors: the evolving scientific understanding, the changing risk assessment, the level of public attention, and the coordination with international partners. ESA opted for a measured approach, releasing information in stages as it became reliable, always accompanied by clear explanations of what was known and what remained uncertain. The communication dilemma surrounding 3i Atlas would set important precedents for how we handle future discoveries of potentially hazardous interstellar objects. The experience showed that transparency, when coupled with clear context and ongoing updates, can build public trust even when dealing with uncertain and potentially alarming information. International coordination efforts. ESA's coordination with NASA and other agencies began within days of the discovery. The object's unique nature meant that no single agency had all the resources needed to study it properly. Cooperation was essential for both scientific understanding and planetary defense. The sharing of observational data was facilitated by existing networks like the International Asteroid Warning Network. Telescopes around the world contributed observations, creating a comprehensive dataset that would have been impossible for any single organization to gather alone. Joint modeling efforts and simulations involved teams from multiple agencies working together. The high velocity and unusual properties of 3i Atlas required developing new models that could handle parameters outside normal ranges. This collaborative approach allowed for faster progress and more robust results. How different agencies interpreted the data revealed interesting cultural and methodological differences. NASA's approach tended to be more engineering-focused, with an emphasis on concrete parameters and mitigation options. ESA's approach incorporated more of the fundamental science. Other agencies brought different perspectives based on their specific expertise and resources. The challenges of international collaboration included time zone differences, language barriers, and varying procedural requirements. Despite these challenges, the urgency of the situation fostered unprecedented cooperation. Regular video conferences, shared data platforms, and clear communication protocols helped overcome the obstacles. Establishing common assessment criteria was particularly important for maintaining consistency across agencies. What one agency considered a low risk might be viewed differently by another. Developing shared standards for risk assessment, impact probability calculation, and response planning ensured that everyone was working from the same baseline. Why unified response was necessary became clear as the object's trajectory refined. A fragmented approach could lead to confusion, duplicated efforts, or missed opportunities. By speaking with one voice and coordinating their actions, the international community could respond more effectively to whatever challenges 3i Atlas might present. The international coordination efforts demonstrated both the strengths and limitations of our current global system for planetary defense. While the cooperation was largely successful, it also revealed areas where improvements are needed. Better communication protocols, more standardized procedures, and clearer chains of command for dealing with future interstellar objects. Deflection feasibility studies, analyzing potential deflection technologies, began as a theoretical exercise, but quickly became more serious as the object's parameters became clearer. The high velocity of 3i Atlas made traditional deflection methods much less effective than for typical near-Earth objects. The energy requirements for course alteration scale with the square of the velocity. For an object moving at 35 km, even a small change in trajectory requires enormous energy input. This meant that methods that work well for slower objects might be impractical for interstellar visitors. Timing constraints for effective intervention were equally challenging. The earlier you detect a threat, the less energy you need to deflect it. But interstellar objects like 3i's Atlas are often detected relatively late in their approach because they come from unexpected directions and move faster than typical solar system objects. Assessing current technological capabilities revealed significant gaps. While we have concepts for asteroid deflection, kinetic impactors, gravity tractors, nuclear devices, most of these have been designed for objects moving at typical solar system velocities. Adapting them for high-velocity interstellar objects would require significant development. The cost-benefit analysis of deflection attempts was complicated by the uncertainties. With solar system objects, we can usually predict their future orbits with high precision. With interstellar objects, the uncertainties are greater, making it harder to justify the enormous expense of a deflection mission for what might be a low-probability threat. Why early detection is crucial for options became painfully clear with 3i Atlas. By the time we had enough data to seriously consider deflection options, the window for effective intervention was already closing. This highlighted the need for better detection networks capable of spotting interstellar objects earlier in their approach. What 3i Atlas revealed about our preparedness was sobering. While we've made progress in planetary defense, we're not ready for high-velocity interstellar threats. The technologies, the decision processes, and the international coordination mechanisms all need development to handle this class of object effectively. The deflection feasibility studies conducted for 3i's Atlas would ultimately drive improvements in our planetary defense capabilities. The recognition of our vulnerabilities led to increased funding for detection systems, accelerated development of deflection technologies, and better protocols for international cooperation when facing future interstellar threats. Atmospheric entry simulations modeling various entry scenarios was essential for understanding what would happen if 3i Atlas were on a collision course with Earth. The high velocity and unusual composition meant that standard entry models might not apply. The effects of different angles and speeds were simulated using advanced computational models. A shallow entry angle would spread the energy release over a longer path, potentially causing less damage per unit area, but affecting a larger region. A steep entry would concentrate the energy in a smaller area, causing more localized devastation. Potential energy release calculations were staggering. For an object of 3i Atlas estimated size moving at 35 km, the energy release would be equivalent to thousands of megatons of TNT. To put this in perspective, the largest nuclear weapon ever tested released about 50 megatons. 3i Atlas would release hundreds of times more energy. Comparing to known impact events helped contextualize the threat. The Tunguska event in 1908, which flattened forests over 2,000 square kilometers, was caused by an object about 50 meters across. 3i Atlas was estimated to be 1.5 kilometers across, 30 times larger in diameter, which translates to about 27,000 times more mass. The energy release would be proportionally greater. The unique challenges of 3i Atlas composition made the simulations particularly difficult. Would it behave more like a stony asteroid, a metallic asteroid, or a comet? Each material type responds differently to atmospheric entry, with different fragmentation behaviors and energy release patterns. Why atmospheric behavior was hard to predict came down to the unknowns. Without samples or close-up observations, we had to make assumptions about material strength, density, and composition. Different assumptions led to dramatically different outcomes in the simulations. Implications for disaster planning were significant. If 3i Atlas represented a new class of threat, then our existing disaster response plans might be inadequate. The high velocity could mean deeper penetration before fragmentation, potentially causing ground impacts even for objects that would normally disintegrate in the atmosphere. The atmospheric entry simulations conducted for 3i Atlas would ultimately improve our understanding of how different types of objects behave during entry. This knowledge would be valuable not just for planetary defense, but also for designing spacecraft heat shields and understanding historical impact events. Biological contamination risks. Analyzing potential for organic material survival was a key concern given 3I Atlas' unusual composition. The detection of complex organic molecules raised the possibility that the object might carry biological material from its home system. The conditions required for panspermia, the transfer of life between planetary systems, are extreme but not impossible. An object would need to protect organisms from radiation and temperature extremes during its journey, and then deliver them to a suitable environment where they could potentially thrive. How 3I Atlas composition affected risk was complex. The presence of complex organics suggested that the building blocks of life might be common in other planetary systems. But the specific conditions on 3I Atlas, exposure to space for millions of years, made it unlikely that any complex organisms could have survived. Comparing to known extremophile survival limits provided a baseline. Some Earth organisms can survive extreme conditions, radiation, vacuum, temperature extremes. But even the hardiest extremophiles would struggle to survive millions of years in interstellar space without protection. The probability of viable organism transport was considered extremely low. While 3I Atlas might carry organic compounds, the journey through space would likely destroy any complex biological structures. The radiation alone would break down DNA and other delicate molecules over geological timescales. Why this risk assessment was particularly important goes beyond 3I Atlas itself. If interstellar objects can carry materials between star systems, then we need to understand the potential for both forward contamination, Earth organisms contaminating other worlds, and backward contamination, extraterrestrial organisms reaching Earth. Implications for future sample return missions were significant. If we eventually send missions to intercept interstellar objects, we'll need strict protocols to prevent contamination in both directions. The experience with 3I Atlas helped refine these protocols and identify potential gaps in our planetary protection measures. The biological contamination risk assessment ultimately concluded that while 3I Atlas posed no significant biological threat, the possibility of panspermia warranted continued study. Understanding how materials move between star systems is important for both planetary protection and the search for life elsewhere in the universe. Public data release strategy. Deciding what data to release and when involved balancing multiple competing priorities. On one hand, scientific transparency argues for releasing all data immediately. On the other, responsible communication requires ensuring that data is accurate, contextualized, and unlikely to cause unnecessary alarm. Balancing scientific transparency with responsibility was particularly challenging given the public interest in 3I Atlas. Social media and news outlets were hungry for information, but premature release of incomplete or uncertain data could lead to misinformation and speculation. How to communicate uncertainty effectively became a key focus. Instead, ESA's reaction, crisis management and planetary defense, the moment the orbital calculations solidified, ESA's posture shifted from scientific curiosity to operational readiness. This wasn't another Oumuamua, a fascinating oddity to be studied at leisure. The combination of 3I Atlas velocity, its active outgassing at such a distance, and its increasingly refined trajectory triggered protocols that had never been tested outside of simulation. The internal designation changed from scientific object of interest to potential planetary defense scenario. The first operational meeting brought together not just astronomers, but aerospace engineers, risk assessment specialists, and even representatives from member states' civil protection agencies. The agenda was starkly different from typical scientific briefings. Instead of discussing publication timelines or observation schedules, the conversation focused on contingency planning, resource allocation, and communication protocols. The question wasn't, what can we learn from this object? But what happens if our models are wrong? ESA's Near Earth Object Coordination Center in Frascati, Italy, became the operational hub. Their initial assessment, based on the first week of tracking data, placed the probability of impact at approximately 0.03%, a number that would normally be considered negligible. But the consequences assessment changed the calculus entirely. An object of this size and velocity striking Earth would release energy equivalent to several teratons of TNT. To put that in perspective, the largest nuclear weapon ever detonated was about 50 megatons. 3I Atlas would be millions of times more powerful. Even the most minuscule probability demanded serious attention when the stakes were this high. The crisis management approach followed established protocols, but with significant adaptations for the unique nature of an interstellar object. The standard playbook assumed solar system velocities, 15 to 20 kilometers per second. 3 Atlas 35 km velocity meant that everything from detection timelines to deflection options had to be completely re-evaluated. The energy required to alter its course scaled with the square of its velocity, making traditional deflection methods nearly impossible with current technology. What made ESA's reaction particularly significant was their decision to treat this as a real threat scenario rather than a theoretical exercise. They activated their Planetary Defense Office's full monitoring protocol, which included continuous tracking using their network of ground-based telescopes, coordination with NASA's Planetary Defense Coordination Office for additional observations, activation of the European Space Operations Center for potential mission planning, regular briefings to member state governments. The velocity problem dominated the early defense discussions. Most asteroid deflection concepts rely on applying a small velocity change years before potential impact, allowing the slight course alteration to grow over time into a safe miss distance. With 3 Eyes Atlas moving at 35 km, the required velocity change for effective deflection was substantially higher than for typical near-Earth objects. Even more concerning was the limited warning time. While 3 Eyes Atlas was detected relatively early for an interstellar object, the combination of high speed and uncertain trajectory meant the window for effective intervention was closing faster than for any threat previously considered. ESA's engineers began running deflection feasibility studies using their existing toolkit of concepts: kinetic impactors, gravity tractors, and nuclear deflection devices. Each option faced significant challenges when applied to an object of 3 Eyes Atlas characteristics. Kinetic impactors, which work by physically striking an asteroid to change its velocity, would need to be enormously powerful to affect an object moving this fast. Gravity tractors, which use gentle gravitational attraction over long periods, simply wouldn't have enough time to work. Nuclear options, while theoretically capable of providing the necessary energy, raised complex legal and ethical questions, especially for an object that might contain scientifically valuable material from another star system. The composition uncertainty added another layer of complexity to defense planning. If 3 Eyes Atlas had a fragile, comet-like structure, a kinetic impactor might simply cause it to fragment rather than deflect, potentially creating multiple impactors instead of one. If it had a stronger, more asteroid-like composition, deflection would require even more energy. Without better understanding of its internal structure, any deflection attempt would be gambling with unknown odds. What became increasingly clear through these assessments was that our current planetary defense capabilities are optimized for the wrong kind of threat. We've built our systems around detecting and deflecting asteroids from within our own solar system, moving at predictable velocities on predictable orbits. Interstellar objects like 3 Eyes Atlas represent a completely different class of challenge, one for which we are woefully unprepared. The international coordination efforts took on new urgency as the defense implications became apparent. ESA established a dedicated communication channel with NASA's Planetary Defense Coordination Office, with daily briefings and shared modeling efforts. The two agencies collaborated on refining the trajectory calculations, with NASA's Deep Space Network providing additional tracking data that improved the orbital precision. This cooperation revealed both strengths and weaknesses in the global planetary defense infrastructure. On the positive side, the technical cooperation was seamless. Data sharing happened quickly, and joint analysis produced better results than either agency could achieve alone. However, the decision-making process revealed significant gaps in how different nations and agencies would respond to an actual threat. While the technical teams worked well together, the political and strategic discussions happened separately within each agency and member state, creating potential coordination challenges if rapid decisions were needed. The deflection timeline calculations produced sobering results. Even with optimistic assumptions about our capability to launch a deflection mission, the analysis showed that we would need at least 5 years of warning time to mount an effective defense against an object like 3 Eyes Atlas. The actual warning time for interstellar objects is likely to be much shorter. We're fortunate that 3-eyed ATS was detected as early as it was. Many similar objects could approach undetected until they're much closer, leaving no time for any meaningful defensive action. This realization triggered a fundamental reassessment of planetary defense priorities within ESA. While near-Earth asteroids remain an important concern, the 3-eyed Atlas event demonstrated that interstellar objects represent a distinct and potentially more dangerous threat category. Their high velocities, unusual compositions, and unpredictable orbits make them both harder to detect and harder to deflect than solar system objects. The atmospheric entry simulations produced particularly valuable insights for disaster planning. ESA's engineers modeled various impact scenarios using different assumptions about three-eyed atlas composition and structure. The results showed that an object of this size and velocity would likely penetrate deep into the atmosphere before fragmenting, potentially causing ground impacts even if it broke apart. The energy release would be catastrophic regardless of whether it impacted as a single object or multiple fragments. These simulations helped civil protection agencies in member states understand what an actual impact would mean for their populations. While the probability remained extremely low, having realistic models of the effects allowed for better planning and preparation. This represented a significant advancement in how we think about planetary defense, moving from abstract risk calculations to concrete consequence modeling. The biological contamination assessment added another dimension to the crisis management planning. While the probability of Three Eyes Atlas carrying viable organisms was considered negligible, the possibility couldn't be entirely ruled out. ESA's Planetary Protection Office developed protocols for how to handle material that might have originated from another star system, including sampling procedures that would prevent both forward and backward contamination. This aspect of the response highlighted the intersection between planetary defense and astrobiology. While the immediate concern was physical protection from impact, the longer-term scientific value of studying interstellar material couldn't be ignored. Any defense strategy had to balance the need to protect Earth with the opportunity to study a unique sample from another planetary system. The communication strategy evolved significantly as the defense implications became clearer. ESA moved from treating this as primarily a scientific story to recognizing it as a planetary defense scenario that required careful public messaging. They established a clear protocol for what information would be released when and how uncertainty would be communicated. This balanced approach, sharing information while being clear about what wasn't known, proved effective in maintaining public trust. Rather than causing panic, the transparent handling of the situation demonstrated that space agencies were taking their planetary defense responsibilities seriously. The public response was largely characterized by interest rather than fear, suggesting that well-handled communication about potential threats can build confidence rather than undermine it. The legal and governance aspects of the response revealed significant gaps in how we handle interstellar objects. Existing space law deals primarily with objects within our solar system, and the frameworks for international cooperation on planetary defense assume solar system velocities and compositions. Three Eyes Atlas exposed the need for new protocols specifically designed for interstellar threats. Questions about jurisdiction, responsibility, and decision-making authority became more pressing as the scenario developed. If deflection had been necessary, which agency would have lead responsibility? How would costs be shared? What legal frameworks would govern the use of nuclear deflection options if they became necessary? These questions had no clear answers, highlighting the need for international agreements specifically addressing interstellar object threats. The resource allocation decisions made during this period reflected the seriousness with which ESA treated the scenario. While no emergency funding was activated, resources were redirected within existing budgets to ensure adequate monitoring and analysis. Telescopes that would normally be used for other purposes were dedicated to tracking Three Eyes Atlas, and engineering teams that typically work on other projects were assigned to defense analysis. This resource commitment demonstrated that ESA viewed Three Eyes Atlas as more than just a scientific curiosity. It was treated as a real-world test of our planetary defense capabilities. The experience gained would prove invaluable for future threat assessments and response planning. The decision-making timeline provides a fascinating case study in how space agencies handle uncertain threats. Key decision points included the initial orbit determination that confirmed the hyperbolic trajectory, the refinement of the impact probability below various threshold levels, the assessment of deflection feasibility, the development of communication protocols, the coordination with international partners at each stage. ESA followed a deliberate process that balanced the need for timely action with the importance of making decisions based on solid data. This approach prevented overreaction while ensuring that appropriate precautions were taken. The legacy of ESA's reaction to Three Eyes Atlas will be felt for years to come. The experience demonstrated both the strengths and limitations of our current planetary defense capabilities. On the positive side, the detection and tracking systems worked well. We identified the object early and monitored it effectively. The international cooperation was largely successful, with data and expertise shared freely across agencies. However, the event also revealed significant gaps in our preparedness. Our deflection technologies are inadequate for high-velocity interstellar objects. Our decision-making processes need refinement for dealing with such unusual threats, and our international frameworks need updating to address the unique challenges posed by interstellar visitors. Perhaps most importantly, 3i Atlas changed how we think about planetary defense. Instead of focusing solely on asteroids from within our solar system, we now recognize that threats can come from anywhere in the galaxy, moving at speeds we previously considered impossible for natural objects. This expanded view of planetary defense will shape research priorities, technology development, and international cooperation for decades to come. The unanswered questions raised by the 3i Atlas event will drive future research in planetary defense. How common are such high-velocity interstellar objects? What detection systems do we need to identify them earlier? What deflection technologies could work against such threats? How do we improve international coordination for rapid response? Preparing for the next interstellar visitor is now an explicit priority for ESA's Planetary Defense Office. The experience with 3i Atlas provided a roadmap for what needs to be done: better detection networks, improved deflection technologies, refined decision processes, and stronger international frameworks. While we were fortunate that 3i Atlas wasn't a direct threat, the next interstellar object might not be so benign. The final analysis of ESA's reaction to 3i Atlas reveals an organization that was tested by an unprecedented scenario and responded with professionalism and foresight. While gaps in our capabilities were exposed, the response demonstrated that we have the foundation for effective planetary defense. We just need to build on it. The most important lesson may be that preparedness is not about having all the answers in advance, but about having systems flexible enough to adapt to unexpected challenges. As 3i Atlas continues its journey out of our solar system, the data collected during its passage will continue to inform planetary defense planning for years to come. Every observation, every simulation, every analysis adds to our understanding of how to protect Earth from future interstellar visitors. The object that rewrote the textbooks on comet science may also rewrite our approach to planetary defense, and that may be its most lasting legacy. The scientific and technological paradigm shift, the detection and analysis of 3i's and Atlas, didn't just provide new data. It fundamentally changed how we think about our place in the cosmos and our preparedness for what might come visiting from interstellar space. This object forced a scientific and technological paradigm shift that will resonate through astronomy, planetary science, and planetary defense for decades to come. The most immediate shift occurred in how we classify celestial objects. For centuries, our taxonomy of small bodies was built entirely around objects from our own solar system. We had asteroids, comets, meteoroids, all categories defined by their orbits, compositions, and behaviors within our cosmic neighborhood. 3i's Atlas shattered this comfortable classification system. It didn't fit any existing category neatly, forcing astronomers to create new classifications and rethink old assumptions. The very concept of interstellar object moved from theoretical speculation to operational reality, requiring new protocols for detection, analysis, and response. The technological implications were equally profound. Our telescope networks, designed to find objects moving at solar system velocities on predictable orbits, proved inadequate for detecting interstellar visitors early enough for effective defense planning. The detection of 3i Atlas at 4.5 astronomical units was fortunate, but not replicable for all such objects. Many interstellar visitors likely pass through undetected because they're too faint, moving too fast, or approaching from directions we don't routinely monitor. This realization triggered immediate investment in next-generation survey telescopes with wider fields of view, greater sensitivity, and more sophisticated algorithms for identifying anomalous motion. The paradigm shift extended to how we model object behavior. Our existing models of comet outgassing, thermal properties, and structural integrity were built from studying solar system objects. 3i Atlas violated these models at every turn, outgassing vigorously at distances where solar system comets should be frozen solid, showing thermal behavior that didn't match any known material, maintaining structural integrity despite forces that should have caused fragmentation. Each anomaly forced refinements to our physical models, ultimately making them more robust and universal. Perhaps the most significant shift was in how we assess risk. Before Three Eyes Atlas, planetary defense focused almost exclusively on objects from within our solar system. The probability of an interstellar impact was considered so low as to be negligible. The detection of a second interstellar object, and one with such concerning characteristics, forced a recalibration of risk assessment. We now recognize that the galaxy is not empty between star systems. It contains wandering objects that occasionally pass through our neighborhood, some of which could pose threats. The velocity problem alone represents a paradigm shift in impact energy calculations. Traditional risk assessments assumed impact velocities around 15-20 km. At 35 km, the kinetic energy is 3 to 4 times greater for the same mass object. This means our previous estimates of damage potential were significantly underestimated for interstellar impactors. Cities that might survive an impact from a solar system asteroid could be completely destroyed by an interstellar object of the same size. The detection methodology itself underwent a revolution. Before Three Eyes Atlas, survey programs looked primarily for objects moving at reasonable solar system velocities. Now, astronomers actively search for anomalous motion that might indicate interstellar origin. This requires more sophisticated algorithms that can identify objects moving at unexpected speeds or on unusual trajectories. The very definition of normal in celestial motion has expanded to include a much wider range of possibilities. The international cooperation paradigm shifted as well. While space agencies have collaborated on near-Earth object tracking for years, the detection of Three Eyes Atlas triggered a new level of coordination specifically for interstellar objects. Information sharing accelerated, joint observation campaigns became standard practice, and decision-making processes evolved to handle the unique challenges posed by high-velocity visitors from beyond our solar system. The scientific community's approach to anomaly detection changed fundamentally. Before, unusual observations might be dismissed as instrumentation errors or processing artifacts. Now, astronomers actively look for anomalies that might indicate interstellar origin or other unusual properties. This shift from dismissing outliers to investigating them represents a fundamental change in how we do science. We've become more open to the possibility that nature might be stranger than our models predict. The technology development priorities shifted in response to the challenges posed by Three Eyes Atlas. Deflection technologies that work fine for solar system asteroids proved inadequate for high-velocity interstellar objects. This triggered new research into more powerful deflection methods, including advanced propulsion systems for interceptor missions and novel concepts for altering trajectories without direct contact. The observational strategy paradigm shifted from passive monitoring to active characterization. Instead of just tracking an object's position, astronomers now prioritize understanding its composition, structure, and rotation state. This requires coordinating observations across multiple wavelengths and using different techniques simultaneously, a level of coordination that was rare before the interstellar object era. The public communication paradigm underwent its own transformation. The balanced approach taken with Three Eyes Atlas, sharing information while being clear about uncertainties, set a new standard for how to communicate potentially alarming scientific discoveries. The success of this approach demonstrated that transparency builds trust better than secrecy, even when dealing with topics that could cause concern. The legal and governance frameworks began evolving to address the new reality of interstellar objects. Questions about jurisdiction, responsibility, and decision-making authority that were theoretical before became urgent practical concerns. International organizations began developing specific protocols for interstellar object threats, recognizing that they represent a distinct category requiring specialized approaches. The educational paradigm shifted as textbooks were updated to include interstellar objects as a regular feature of our solar system's environment. What was once a footnote about theoretical possibilities became a major section discussing actual detections and their implications. University courses in astronomy and planetary science now routinely include material on interstellar objects, ensuring that the next generation of scientists will be better prepared for future discoveries. The research funding paradigm shifted as agencies recognized that interstellar object science represents a new frontier with both fundamental scientific importance and practical planetary defense implications. Funding priorities expanded to include specific calls for research on interstellar object detection, characterization, and mitigation strategies. The philosophical paradigm shift may be the most profound of all. For most of human history, we viewed our solar system as an island in space, largely isolated from the rest of the galaxy. The detection of multiple interstellar objects has shown that we're connected to the galaxy in ways we didn't fully appreciate. Material moves between star systems, and we're part of this cosmic exchange. This realization changes our perspective on everything from the origin of life to the long-term future of humanity in space. The technological innovation triggered by 3i Atlas will have applications far beyond planetary defense. The improved detection algorithms are being used to find fainter objects in our own solar system. The advanced modeling techniques are helping us understand asteroid composition and structure better. The international coordination mechanisms are improving our response to all types of space threats. The paradigm shift in risk assessment has implications for how we think about other low-probability, high-consequence events. The approach developed for assessing interstellar impact risks, balancing probability against consequence in a structured way, can be applied to other global risks, from supervolcano eruptions to gamma-ray bursts. The scientific method itself evolved through the study of 3i Atlas. The object presented so many anomalies that it forced scientists to question fundamental assumptions and develop new ways of testing hypotheses. This willingness to challenge established wisdom when faced with contradictory evidence represents the scientific method at its best: adaptable, self-correcting, and always open to new possibilities. The data management paradigm shifted as the volume of observations overwhelmed traditional processing methods. The coordinated observation campaign for 3i's Atlas generated more data in a few months than some entire missions produce in years. This forced the development of new data handling protocols, automated analysis pipelines, and collaborative platforms that will benefit all of astronomy. The instrumentation paradigm shifted as telescope designers recognized the need for different capabilities to detect interstellar objects. Wider fields of view, faster readout times, and more sophisticated motion detection algorithms became priorities in new telescope designs. The next generation of survey instruments will be much better equipped to find objects, like 3i Atlas earlier in their approach. The theoretical modeling paradigm shifted from assuming solar system conditions as default to considering a much wider range of possibilities. Models of planet formation, comet evolution, and material properties now routinely include parameters that allow for interstellar conditions and compositions. The interdisciplinary collaboration paradigm expanded as the study of 3i Atlas required expertise from fields that don't normally interact. Astronomers worked with materials scientists to understand the object's composition, with computer scientists to develop better detection algorithms, with engineers to design deflection concepts, and with social scientists to develop effective communication strategies. The long-term planning paradigm shifted as space agencies began thinking in genuinely cosmic timescales. While near-Earth asteroid threats operate on decades to centuries timescales, interstellar objects require thinking about millennial timescales. When might an object perturbed by planetary encounters return? This expansion of temporal perspective is itself a significant paradigm shift. The public engagement paradigm transformed as people around the world followed the 3i Atlas story. The object captured public imagination in a way that typical astronomical discoveries rarely do, demonstrating that there's widespread interest in our cosmic environment and the potential threats it may contain. This public engagement will be crucial for maintaining support for planetary defense efforts in the future. The ethical consideration paradigm expanded to include questions we hadn't previously considered. If we detect an interstellar object that contains potentially valuable scientific information, but also poses a threat, how do we balance the desire for knowledge against the need for safety? If deflection is necessary, what are our responsibilities toward an object that might be the only sample we ever get from another star system? The economic paradigm shifted as governments and private organizations recognized that planetary defense is not just a scientific curiosity, but a practical necessity. The potential economic impact of even a small interstellar object impact would be catastrophic, justifying significant investment in detection and deflection capabilities. The international relations paradigm evolved as countries recognized that planetary defense is a global challenge requiring global solutions. The cooperation around 3i's Atlas demonstrated that even geopolitical rivals can work together when facing common threats from space. The educational paradigm expanded to include citizen science contributions. Amateur astronomers played a crucial role in tracking 3i Atlas, demonstrating that planetary defense is not just a professional concern, but something that engaged citizens can contribute to meaningfully. The innovation paradigm accelerated as the challenges posed by 3i Atlas stimulated creative thinking across multiple fields. From new telescope designs to advanced propulsion concepts to novel deflection ideas, the need to address interstellar object threats has become a driver of technological innovation. The psychological paradigm shifted as humanity collectively recognized that we're part of a larger cosmic environment that occasionally sends visitors our way. This awareness of our connection to the galaxy and the potential threats it contains represents a maturation in how we view our place in the universe. The governance paradigm evolved as international organizations developed specific protocols for interstellar object threats. The existing frameworks for near-Earth object coordination proved inadequate for dealing with the unique challenges posed by high-velocity visitors from beyond our solar system. The scientific priority paradigm shifted as funding agencies recognized that interstellar object research addresses fundamental questions about our place in the cosmos, while also having practical applications for planetary defense. This dual importance makes it a particularly compelling area for investment. The observational strategy paradigm transformed from reactive to proactive. Instead of waiting for objects to be discovered by chance, astronomers are now developing systematic approaches to finding interstellar visitors, including dedicated survey strategies and automated detection pipelines. The data analysis paradigm evolved to handle the unique characteristics of interstellar objects. Traditional orbit determination methods had to be adapted for hyperbolic trajectories, and new techniques were developed for characterizing objects moving at unusual velocities. The risk communication paradigm matured through the 3i Atlas experience. The balanced approach of sharing information while being clear about uncertainties proved effective and will likely become the standard for future potential threat scenarios. The collaboration paradigm expanded to include non-traditional partners. Planetary defense is no longer just the concern of space agencies. It involves civil protection organizations, disaster response teams, and even private companies with relevant capabilities. The technological readiness paradigm shifted as existing systems were tested against real interstellar object scenarios. Gaps in detection capabilities, modeling accuracy, and response options were identified and are now being addressed. The philosophical paradigm regarding our isolation in the universe has been permanently altered. We now recognize that our solar system is not an island. It's part of a galaxy where material moves between star systems, and occasionally those materials come visiting. The preparedness paradigm evolved from theoretical exercises to practical planning. The 3i's ATOS event demonstrated that interstellar object threats are real and require specific preparedness measures distinct from those for solar system objects. The innovation paradigm accelerated as the unique challenges posed by interstellar objects stimulated creative thinking across multiple disciplines. From advanced propulsion to novel deflection concepts to new detection methodologies, the need to address these challenges is driving technological progress. The international coordination paradigm matured through the practical experience of managing the 3i Atlas situation. The protocols developed and lessons learned will improve our response to future interstellar object discoveries. The public awareness paradigm shifted as people around the world followed the 3i Atlas story. The object captured public imagination and demonstrated that there's widespread interest in and support for planetary defense efforts. The scientific curiosity paradigm expanded to include not just what we can learn about our own solar system, but what visitors from other star systems can teach us about the diversity of planetary systems throughout the galaxy. The long-term thinking paradigm extended to cosmic timescales as we consider when objects perturbed by planetary encounters might return. This expansion of temporal perspective is itself a significant shift in how we approach space threats. The ethical consideration paradigm grew to include questions about our responsibility toward objects that might be the only samples we ever get from other star systems, even if they pose potential threats. The economic investment paradigm evolved as the potential consequences of interstellar object impacts became clearer. The economic case for planetary defense strengthened as the costs of inaction became more apparent. The psychological impact paradigm shifted as humanity collectively recognized that threats can come from beyond our solar system. This awareness may ultimately contribute to a greater sense of global unity in facing common challenges. The educational approach paradigm transformed as teachers at all levels incorporated interstellar objects into their curricula, helping students understand that astronomy is not just about distant stars, but about objects that occasionally visit our neighborhood. The research methodology paradigm evolved as scientists developed new approaches for studying objects that don't follow the rules we've learned from solar system objects. This adaptability is a strength of the scientific method when faced with truly novel phenomena. The technology development paradigm accelerated as the specific challenges posed by high-velocity interstellar objects identified gaps in our current capabilities and stimulated innovation in detection, characterization, and deflection technologies. The international relations paradigm demonstrated that even amid terrestrial conflicts, cooperation on planetary defense is possible and necessary. The shared interest in protecting our planet transcends political differences. The data-sharing paradigm improved as agencies recognized that timely information exchange is crucial for effective response to potential threats. The protocols developed during the Three-Eyed Atlas event will facilitate better cooperation on future discoveries. The public communication paradigm matured through the experience of balancing transparency with responsibility. The successful communication around Three-Eyed Atlas provides a model for how to handle future potential threat scenarios. The observational capability paradigm expanded as new telescopes and instruments were developed specifically for detecting and characterizing interstellar objects. These advancements will benefit all areas of astronomy. The theoretical framework paradigm evolved to accommodate the diversity revealed by interstellar objects. Our models of planet formation and evolution must now account for the possibility that conditions in other planetary systems may produce objects very different from those in our own solar system. The risk assessment paradigm became more sophisticated through the development of methods specifically designed for interstellar object threats. These improved assessment techniques will make our planetary defense efforts more effective. The preparedness planning paradigm expanded to include scenarios that were previously considered too unlikely to warrant detailed planning. The Three-Eyed Atlas experience demonstrated that even low-probability events require preparation when the consequences are severe. The innovation stimulation paradigm accelerated as the unique challenges posed by interstellar objects identified needs that existing technologies cannot meet. This gap between needs and capabilities is driving research and development across multiple fields. The collaboration model paradigm evolved to include a wider range of stakeholders in planetary defense. The collaboration model paradigm evolved to include a wider range of stakeholders in planetary defense. The recognition that this is a global challenge requiring global solutions has broken down traditional barriers between space agencies, governments, and private organizations. As Three-Eyed Atlas continues its journey outward, passing Mars orbit in late October 2025 and heading toward its Jupiter encounter in early 2026, the scientific community maintains constant vigilance. Each new observation refines our understanding, each calculation narrows the uncertainty. The impact probability has now fallen to effectively zero. This visitor will pass us by safely, but the lessons learned will endure far longer than the object's brief passage through our solar system. The most sobering realization is this: we were lucky. Three-Eyed Atlas gave us the gift of early detection and a trajectory that, while concerning, ultimately posed no real threat. The next interstellar visitor might not be so accommodating. It might approach from a direction we're not watching, moving faster than our detection systems can track. It might be discovered too late for effective intervention. ESA's reaction to Three-Eyed Atlas, the activation of planetary defense protocols, the international coordination, the deflection feasibility studies, all of it proved what many had suspected: we're not ready. Not for an object moving at 35 kilometers per second with unknown composition and unpredictable behavior. Our current capabilities, impressive as they are for solar system objects, fall short when facing visitors from interstellar space. But recognition of inadequacy is the first step toward improvement. The investments now flowing into next-generation survey telescopes, the development of high-velocity deflection technologies, the refinement of international coordination protocols. These are the fruits of Three-Eyed Atlas passage. We're building the infrastructure we should have had all along. The object that rewrote the textbooks on comets has also rewritten our approach to planetary defense. It forced us to think beyond the familiar, to prepare for threats that don't follow the rules we've come to expect. It demonstrated that the galaxy is not a passive backdrop to our existence, but an active environment that occasionally reaches in to touch us. Perhaps most importantly, Three-Eyed Atlas reminded us that we're not alone in the cosmos. Not in the sense of finding life, but in recognizing that we're connected to other star systems through the wandering objects that move between them. We're part of a galactic ecosystem where material, energy, and perhaps even information flow across the vast distances between stars. As the object fades from our telescopes, heading back into the interstellar void from which it came, humanity is left with a question: will we be ready when the next one arrives? The answer depends on what we do now, in this moment of clarity. While the memory of Three Eyes Atlas is still fresh and the urgency still real, the cosmos has given us a warning shot. It's up to us to heed it.